And even when you go to 100% renewable, you know what's working in the background.
Wait, say that again?
When you go to 100% renewable generation, you know what's working in the background.
What?
You have to have a battery. You have to have something that can maintain voltage and frequency, something that can steady or absorb the variation. Even if you're operating at 100%, there is some variability in wind and solar.
Cloud, a wind speed.
Well,
welcome to the world-changing podcast.
Was that too much? Yeah, that was probably too much. But let's keep it. We'll keep it anyway. How about this? If we do the podcast and the world doesn't change, then we can take that out. Welcome to the World Changing Podcast, where we deconstruct the projects and products that are moving us towards a decentralized and carbon-free future. We'll talk to the skeptics, supporters, and innovators in the fields that depend on electricity to run their industries, which is changing every single day. I'm your host, Greg Robinson, co-founder of Aston Labs, a decentralized infrastructure company. And on the other side of the camera here, we have Flo Lumsden, our producer, and she will make sure that the train stays on the tracks while we do this. Okay, everybody, I am so excited for this episode. We have Gary Rackliffe. Gary Rackliffe is the Vice President of Market Development and Innovation at Hitachi Energy. Hitachi Energy is responsible, or at least their technology underlies, half of the top 250 power utilities in the world. I met Gary through a project that Aston Labs is working on. It's one of those projects where, and I guess we talk about it a little bit in the episode conceptually, where we're trying to do some really big industrial applications with zero fossil fuels and very high uptime at an affordable price, because industrial customers won't stand for anything else. You know, when you're going to do something that complex, you're bringing in people like Gary Rackliffe. That's how we met. I mean, obviously hold him in very high esteem, his team and the company. Up until recently, it was called ABB, and I've known ABB since the minute that I walked into the electricity industry. The grid. How do you decarbonize the grid? One of the biggest pieces that's missing from this conversation of getting rid of fossil fuels, getting rid of carbon on our grid, is transmission. We're starting to see articles about it. Even today in the New York Times, we've seen it in The Economist. And this missing piece is transmission. So we have Gary Rackliffe to talk about that piece. The grid. It's one of the most complex machines that we've ever built. We have complex problems, which obviously is going to include complex answers. And Gary helps us pick apart all of these pieces. In this episode, Gary's going to give us this real story of his career evolution, but we need to start with his list of credentials. Gary currently holds the position of the VP of Market Development and Innovation for North America at Hitachi Energy. Gary focuses on the energy transition, modernizing the grid, is an industry leader and serves as the expert advisor to utilities, government agencies, and industry associations on the best practices for clean energy, grid modernization, smart grids, and digitalization. Gary is a member of the Renewable Energy and Energy Efficiency Advisory Committee for the Department of Commerce. He's on the GridWise Alliance Technical Council, the E4 Carolinas Innovation Council, and the International Electrotechnical Commission's Smart Energy Systems Committee, where he serves as a technical advisor. Gary holds a bachelor's degree in electric power engineering from RPI and an MBA from Carnegie Mellon. He's a registered professional engineer, IEEE Senior Member, has co-authored a transmission and distribution planning book, and has written numerous technical papers and articles on the topic.
Why has it been a big deal to get Gary on the show?
The reason it was a big deal to get Gary on the show probably stems from some kind of like deep insecurity of my own, which is that a lot of circles that I'm in, people ask me questions about electricity and I'm supposed to have the answers. And then when I talk to Gary, I feel like I have no answers. I just have questions. And it's been a big deal to have Gary on the show. Obviously, I'm excited to ask these questions, but then also just like, I don't think I've been as nervous to have to record somebody on the podcast as I was for Gary, because I was just like, man, some of these topics are so deep and complex, and I don't want to lose that complexity. Yeah, that's why.
And I love, once I really wrap my head around the terms that I'm going to share in this intro, I could follow along. Maybe not to the degree someone who's in this industry all the time could, but I learned a lot. And I think that's empowering as someone who wants to support efforts to make the grid more environmentally friendly, more efficient, and smarter. It's empowering to know what our options are and if there's an opportunity to support those. So I hope that folks who aren't in the industry will also try to get through this with us, because it's a great learning opportunity.
Yeah. That was a good spot. Flo's going to help us with some definitions, and I hope you enjoyed the episode.
All right. So one of my goals for this show is to make these conversations a little bit more followable for anyone like me who may not be in the industry but wants to learn. So I wanted to define a few terms. These are also in the show notes. We talk a lot about transmission and distribution in this conversation. So a transmission line carries electric energy from one point to another in an electric power system. They can also carry alternating current or direct current, or a combination of both. Transmission lines are important for moving energy around. HVDC, or a high voltage direct current electric power transmission system, offers long distance power transmission, improved integrity of renewable energy, and the ability to connect different power grids together. Solar PV. So PV stands for photovoltaic, and it gets its name from the process of converting light photons to electricity, which is also called the photovoltaic effect. This is another fancier way to describe solar power. Load versus generation. Load is another word for the demand for electricity on the power grid at any given time. Or it's the total electricity being consumed or removed from the grid by the users of the grid. Dispatchable power versus non-dispatchable power comes up a lot in this conversation as well. These two terms refer to the ability of a power source to be controlled and adjusted to meet fluctuating demand for electricity. Dispatchable power sources currently include fossil fuels, hydrogen, geothermal, and biomass power. Non-dispatchable power, also known as intermittent or variable sources, are those that cannot be easily controlled or scheduled to match the electricity demand. Examples include solar power, wind power, wave, and tidal power. These fall into the non-dispatchable category because their availability is influenced by weather conditions and natural phenomenon. We talk a lot about gigawatts of power. So how much can 1 gigawatt power? How can we think about that in everyday terms? So 1 gigawatt is enough to power about 7,500,000 homes, or 750,000 homes can be powered by 1 gigawatt. I like to keep that in mind because when we're throwing around 13 gigawatts of power, that's a lot of power. Lastly, 100% uptime refers to the reliability of the power supplied. It is referring to perfect or near perfect reliability with no power outages. All right, let's get going.
You've spent, is it fair to say you've spent all of your career in power, in
Probably fair.
power grid? I was just gonna stop and be like, why? No, as I always have to ask everybody this question. What was there something as a kid that you did, or that you were exposed to, or that your parents did, or they exposed you to, that kind of prepared you or led you into what you do today? And that can be what led you to going into power grid work, or even for today. Is there something that you were exposed to as a kid that helps you in this? I mean, there's a lot of change right now in this industry, I'm assuming, from when you,
it makes
when
it
you got
exciting
into
today.
it. Right, yeah. Is there anything that you can point to in your younger years that led you to this?
I'm not sure. Maybe. My father was an electrician.
Okay.
When I was in school, did well in what people now call STEM courses. So a logical, I guess, career path for me was to go to an engineering school and get an engineering degree.
Yeah.
And I decided, since my father was an electrician, maybe I would focus on electrical engineering.
Yeah.
But I made a decision early on, once I was at the college where I did my undergraduate work. In electrical engineering, there's electronics, and then there's everything else.
Right. Yeah.
I guess this happened because of, again, my father. He was very focused on getting job experience. And when I graduated from college, he absolutely wanted me to have a job so that I'd be office payroll, gainfully employed, cost recovery, if you will, on
Right.
the cost of the tuition. He was all in on that. I think he might have been happier if I'd gone to a school in Boston that had mandatory co-op jobs. So as a freshman, he insisted that I go to the co-op office and sign up. And I told him, they don't interview freshmen. Freshmen don't get co-op jobs.
Yeah.
As it turned out, I was wrong and he was right. So I did go to the co-op office. I did fill out the form, and as a freshman, and the person in the office said, "Oh, do you want to meet our co-op advisor?" Not the guy who ran it, but he was the assistant co-op program director at the school. And I said, "I'm a freshman." She said, "Oh, he's available. Why don't you go in and meet with him?" So I went and talked with him, and I talked about what I was doing and that I was basically focusing on electrical engineering, but hadn't really decided on electronics or power. But as it turned out, who knew? He actually knew my father rather well, and actually knew me at that time 15 years when I was like 3 years old.
Wow. Yeah.
And didn't think much of it. I said, "Yeah, I'll mention to my dad I saw you and talked with you, and I'll tell him you sent your regards." Anyway, I got a call late in my freshman year. "Do you want to go to work for Boston Edison?" which is the utility in the Boston area. It's now part of Eversource. And I did. So I took the fall semester of my sophomore year, and I went to work for a utility and had that early exposure where the program I had, they had me doing everything for going out to test power transformers before they were energized, to checking accuracy of meters, working in one of their yards. And then I went back and worked for them the following 3 summers. And so had a lot of exposure to the power engineering side, which reinforced the program. And as it turned out, the school I went to, I would argue, had the #1 power engineering program literally in the world while I was there. Half of the class my graduate year was foreign students.
Wow.
And went to work for Westinghouse Electric.
And Westinghouse Electric became...
So the Westinghouse Electric T&D company became what was called Westinghouse ABB Power T&D Company. Then they dropped the Westinghouse.
Yep.
And basically became ABB. And then in 2020, ABB and Hitachi formed a joint venture, with Hitachi having majority ownership of that joint venture at 80%. Last December, they bought out the remaining 20%. So where I started, basically that business, that T&D business, continued from Westinghouse to ABB, and now it's 100% Hitachi owned.
Wow. And some things have changed since you started.
A few things have changed, just a few. I think the biggest things that have changed is the digital technologies over the time period. And what we do with computers today, my phone has more power than the computer I used when I first started working.
Yeah.
I think the digital communication technologies, that's transforming our industry. When people ask me what my job title is, market development and innovation. But what I do is I work on the energy transition, and we've talked about that. Decarbonization of generation and decarbonization of energy end-use consumption. But the other part is I focused a lot previously on smart grid technology, which has evolved into grid modernization. One key part of that is resiliency, because climate change, even though we're trying to mitigate it, it's here.
It's here,
And it's impacting utilities. More storms, more severe storms, More trees is an issue, but that issue has been around for a long time.
Maybe more trees coming down.
Yeah, more trees.
Sorry, I just had like trauma of this tree that keeps falling on my house.
Yeah, so trees are an issue. It's actually probably one of the biggest components of grid reliability because most outages for end-use customers occur at the distribution level.
Yeah.
Just more hurricanes, more tornadoes, more flooding, more extreme cold, more extreme heat. All of those are impacting the grid.
Yeah.
And so resiliency is really part of what we call license to operate. You need to be addressing resiliency. You also need to address reliability. A big component of that is aging infrastructure, making sure that your equipment is performing reliably. But then you also have improving efficiency, addressing power quality issues. And the other big issue, which I relate to grid modernization, is just the security piece, both physical and cyber. But in underpinning both grid modernization as well as the energy transition is what we can do digitally. And you didn't ask this, but one of the benefits of being part of Hitachi is we come to the table in Hitachi Energy with the equipment, the systems, ability to service what we sell, et cetera. But Hitachi has an IT component to the company. Hitachi Vantara is what it's called, plus another operation which is called GlobalLogic, which was a recent acquisition, which gives us tremendous IT capability to complement our operational technology. So this thing of IT, OT.
Definition question. OT, operational technology?
And IT is information.
Informational technology.
Yep. We just got a huge booster shot when we joined Hitachi because of their IT capabilities, really to address this concept of digitalization.
So the high-level stats of Hitachi Energy are mind-boggling. When I was looking online, I started seeing these numbers that were insane. So to say that you have some involvement in the power industry is an understatement. What are the high-level stats of Hitachi Energy? How much of the global power grids do you have an impact on, or your technologies are involved in?
So Hitachi Energy is known as being a major supplier, or the major supplier, to the utility market, primarily transmission and distribution. But there's a few areas that we really dominate the market, in my opinion. One is we're the leading global provider of HVDC technology and power quality solutions. So that's really part of our equipment side of our business. Also, we're the number one global supplier of transformers. So these range from power transformers to distribution transformers to traction transformers, for example, for rail applications. But globally, we're the largest supplier of transformers. So the equipment piece of our business is very significant. But that said, we also have IT and software solutions. 50% of the top 250 global utilities use our software.
Half of the 250 largest global utilities
are using our software. We talk about these days IoT, we talk about digitalization, and we have $4 trillion of assets that we're managing and optimizing with our software solutions from our grid automation business. So we're not only the leading equipment provider, the apparatus, the equipment, the breakers, the transformers, but we're also very much focused on digitalization, IT solutions, and optimizing and managing the grid.
Wow. We're going to dig into some of this stuff later, but basically that means when the power grid is running every single day and we're all flipping our lights on whenever we want to do that, your technology is sitting out there making sure that when that happens, these lights come on. We can do podcasts.
Sure, I'd like to say that we're responsible for keeping the lights on, but we provide the infrastructure and we provide the software that enables your local utility provider to make sure that your lights.
Is that the primary customer target, is the utility company, or do you do, like you'd mentioned, rail? Are most of these kind of quasi-governmental agencies that you're working with, or do you have private customers as well?
No, I think there's two parts to our business. One is we do serve the utilities, and to a lesser extent maybe generation, but generation has to connect to the grid. So certainly the utilities are a major part of our customer base, but the other part of our customer base is what I would call energy intensive market verticals. Oil and gas, mining, pharmaceuticals, data centers. These are all energy intensive market verticals. And because of the amount of energy that they consume, they need more infrastructure to be able to deliver and then to manage that on their side of the meter. So that's the other key part of our business. We do provide solutions for electrification of rail and transportation, and then companies that are heavy consumers of electricity, and then also the utilities that are supplying it.
I kind of want to talk about rail, but that's only because I'm curious. I'm going to go to
Rail in the U.S. is not terribly electrified. There's a lot of upside potential for electrifying rail in the U.S. Europe is much higher.
Yeah, being down in North Carolina, when we were thinking of moving to this region, one thing I saw was like, when are we going to get a light rail in this area? And now that I've lived here for a little while, I think the answer is we're not.
I know a little bit about that.
You do?
Well, never say never. It keeps getting looked at, but what would make sense just at a high level? We're in the research triangle, so why don't you connect the 3 points of the research triangle with rail?
Is this happening?
Gary, I'm going to start another podcast looking for funding.
Yes, funding would be a good thing. And then the other thing is, it's got to connect to the airport.
Yeah.
If I could hop on a rail line here in Apex and get to the airport with a light rail solution, even if I had to go into Raleigh and then go back out to the airport,
wouldn't it make a difference? Yeah.
It would be handy. I think a lot of people would select that option of getting to the airport rather than fighting the traffic, particularly when you're being picked up.
But the airport makes all of its money from the parking lot. So that's the
rub.
Therein lies the power dynamic rub that we're coming up against.
They do make money, I'm assuming, from their parking lots and the parking garages.
Yeah.
They're not incentivized to bring.
We need to call the Seattle people. They put a light rail right into the parking lot there. You could take the light rail and walk by all the parked vehicles, and that would be, we don't have to go down the rail rabbit hole, but I do think like electric rail in some of these places, especially just seeing people moving all over the country, there's certain hot spots that are blowing up. Anyway, I digress. Every time that we talk, the concept of HVDC comes up, and I thought what would be interesting is to go back to just some of the big headlines that we've seen come out in Wall Street Journal and New York Times. Is the dream of renewables is being blocked by these lengthy interconnection queues. So first, I know we're going to have to take a huge step back, but what is an interconnection queue, and why is this blocking our renewable dreams from coming true?
So the interconnection queue is basically a queue of companies that want to connect generation resources or assets to the transmission grid. Typically, there needs to be a study to determine if there's sufficient capacity and what would be the impact of connecting that generation to the grid to determine whether or not the grid at that location can accommodate that resource. A study needs to be done, so these get queued up as part of the approval process. So that's what the interconnection queue is.
And it's backed up.
It's worse in some areas than others. It depends upon how many generation resources want to connect to the grid within a particular area. Typically, if it's connecting where there's an independent system operator or an RTO, regional transmission operator, they may have limited resources in terms of processing and evaluating these interconnection requests in order to move forward and connect them into the grid.
And so then that's how it's been done for quite a while, at least. I know that the transmission operators and those were kind of a new thing that came about Was that post deregulation, or was that happening before?
I think it was part of, I guess going back, I think it was part of deregulation, where now instead of having vertically integrated utilities, you had a deregulated infrastructure where you had generation owners, and then you have transmission and distribution wires companies, and they own those assets. And then you have an independent grid operator, an independent system operator responsible for the dispatch of generation, having a market so that you have the most economic dispatch. And then, of course, you have to manage the transmission grid because that's where your constraints come from. Yeah. There's a terminology that's used. It's called security constrained unit commitment.
Security
and the security in this case is security of the transmission grid, security of grid operation. And you want to make sure that when you operate the grid, that you have the ability to withstand single or even potentially double contingencies and still be able to maintain the integrity and the operation of the grid. Because if you lose any one of those pieces, you still need to be able to maintain the integrity and continue to deliver power.
Yeah, that's a hard problem. That, in my life of being in startups or talking sometimes to financiers who know nothing about the power grid, is this one concept that all of these things have to be in perfect balance or very close to perfect balance all the time, every millisecond of every day. And that creates a really interesting economic or market dynamic that doesn't really exist when you can throw something in a warehouse, or you can, like most other markets, if you make something and nobody buys it, it ends up filling up a storage unit somewhere and you shut down the business and no big deal. But in power, you don't even get to make anything for the power grid until it is known that when you push this power onto the grid, that nothing bad is going to happen.
So the cue is to get connected, to have access to the grid. What I mentioned in terms of security and the security constraints, that's the operational decisions that are made to dispatch generation. And you're correct when you said generation and the resources always has to match the load.
Right, yeah.
And so what we may see, it's probably not true today, because today generation follows load, but there may be a time, particularly when we use more and more non-dispatchable generation resources, think wind and solar. We may start thinking about dispatching load to match a non-dispatchable generation profile. What does that look like? That means in California, you may try and shift charging of EVs to 2 p.m. in the afternoon when you have a surplus of solar PV that might otherwise be curtailed. The only thing that injects itself into that equation is storage. And there you can decouple when you generate or how much you generate versus load, because now you're storing energy. Yep. But we don't have that much storage. Yeah. Most of the storage we do have in this country today is pumped hydro.
That's right.
It's over 90% of the storage is pumped hydro, but there's a lot of interest in investment in battery energy storage. And the reason is because it gives you that flexibility. It provides stabilization of variable resources, again, like wind and solar.
So funny how like everything we talk about, whether it's transmission or it's storage or it's demand response, which you mentioned in different words, which is we have the people who are using the power changing how they use the power to match everything. It all comes back to that one thing. Everything has to be in balance. Right. We're all just trying to balance it, and everybody has to work together. The way we met was around this concept of a large industrial campus or microgrid where you could do all of this on site. Conceptually, that is incredible. You could run a data center or something that has this economic value in the economy that has nothing to do with electricity. It's computing storage, or maybe it's industrial warehouses. And then you can power all of that on site. But then when I start getting into the technical weeds, 100% uptime is really hard to achieve. 100% versus 99.9999 is a huge difference in terms of how much more power do we need to build in order to get that last little bit of reliability. And so I'm just curious from your perspective, with zero carbon emissions, no diesel backup, anything, given the technology we have today, can you run a small power grid
Sure, it's all possible and feasible. It's how much would it cost? Your comments, there's a number of things that you touched on. So you're correct. The grid actually did start as a microgrid in today's terminology. And then we saw the expansion of multiple microgrids. If a microgrid only has a sole source of generation, then reliability becomes a concern, because if that generator goes, the whole grid associated with that microgrid basically is down. In theory, two microgrids tied themselves together. And so now you had two microgrids with a link. In the case the generation at one failed, they could rely on the generation of the other. And that was the start of what is today's grid.
Yeah.
And so it really addresses the reliability piece, because as you point out, we have to match generation to load. You can address that reliability through the grid that we have today, the interconnected grid. The other way you can protect yourself is with storage. But storage has a cost associated with it, particularly if you have a diesel generator and you need a part and you can't get the part for 2 weeks. That's really inconvenient if you want to watch, the football game on Sunday afternoon. Or even more important, if you have a mission critical business, what do you put on site in terms of backup storage? You mentioned data centers. The data centers typically have backup on-site power to serve all critical loads. They take their main power from the grid, but they typically have backup on-site resources that can actually maintain the data center for days, if not weeks. But in addition to that, the real critical data centers have a backup for the backup. So dual redundancy.
Yeah.
And then they also may rely on not just one feed from the utility, but they may take a second circuit and a second feed, so they have redundant feeds, all pursuing a level of reliability, whether that's 6 nines or whatever the case may be, that they determine they need for their facility. But redundant feeds cost extra money. Putting in a backup on-site system and maintaining that system, maintaining the fuel, and then putting a backup to that all have expenses, which a data center justifies by need for reliability.
Yeah.
And so can you build a site that has on-site power generation? Sure, but you need to make sure that you have some diversity of generation. You need to make sure that some of that generation is dispatchable, that it's not weather and time dependent if you're trying to achieve those high nines.
Yeah.
Where we first met each other, that particular site is looking at different types of resources.
Yeah.
But it also has access to the grid, so it can use a grid connection as backup. And there's always the possibility of putting in storage to complement the renewable generation that's on site.
Yeah.
And ultimately, all of those combined can achieve the 6 nines of reliability that a large data center would require with mission critical load.
Yeah. Yeah, it's really interesting how it seems that the cloud computing industry, I don't know if it was from the beginning, but at least the first time I ever saw a contract to buy cloud computing services, it's always based on reliability. It's based on how often do you need this on? Can you lose 1 hour a year? Can you lose 10 hours a year? Can you lose 20 hours a year? And you have a rate sheet based on how often you want this thing to stay on. It doesn't seem like in the power industry we have that, but I could be wrong. Do any utilities in the country offer that type of reliability rate sheet? Because I don't have it in my house, of course. They just say, hey, we'll keep the lights on as often as we can.
So I haven't been as involved in the rate sheet and how utilities price reliability.
Yeah.
But if you have an industrial company that has a need for high reliability, it depends where the reliability infrastructure, that on-site generation or that backup storage, which side of the meter is it on? So if it's on the customer side of the meter, the company or the industry is making the investment to ensure that they're making the economic investment on their side of the meter to be able to address their needs and requirements. And it's not just data centers. Pharmaceutical, where you have processes where if you interrupt that process or have a blip in your power, you have to scrap the whole production run, clean out all your machines and start all over again. Really costly. Chip manufacturing, same thing. So reliability has a cost if you don't have it, which means companies are willing to invest in infrastructure on their side of the meter or pay the utility to put infrastructure on the utility side of the meter, that redundant power feed, for example. Basically, they have a utility microgrid with local power, whether it's storage or something that can feed that facility in the event that the main supply through the grid is lost through an outage or some problem. So that price sheet or that rate depends who's doing the investing to provide the level of reliability.
I always have this problem. I blame ever studying physics in my life for this problem, but I always have to follow it out to like the nth degree of what will happen if we keep moving. If this option comes readily available to everyone, to basically where 10 years ago we would have thought, hey, I could put a battery in and this will be my backup power in case the grid goes down. It seems that we may end up gravitating towards this world where you have this private utility or this way of supplying electricity to yourself, and then there's this big grid, which, man, I mean, even this project that we've talked about or that we met on was, we look at the grid as a backup. Like, we don't look at that as the primary source of electricity. We're thinking, okay, we can get this on-site generation, and then the grid ends up being that last little bit of reliability. What's your view on that? Do you think, I know you work with a lot of these utilities, so I'm sure that they don't see it that way.
The utility has a little bit different lens. And look at it from this perspective. Let's suppose that you have a site where on the customer side of the meter, you have generation resources. And let's assume, just for discussion, that those are renewable, so they're variable.
Sure.
You have some storage, but there could be a scenario where you're going to need to pull power from the grid. And so you have your critical loads, and maybe it's 5 megawatts of load. So if you're going to use the grid as backup, that means you need to have a grid connection that can support 5 megawatts of load.
Yeah.
And then the utility that owns the grid that's serving your facility has to be able to deliver, has to have the capacity to be able to deliver 5 megawatts.
Just hanging out.
Whether you use it or not.
Right. Yes.
And so if you're going to require that capacity in the grid as your backup, then the argument is, from the utility point of view, you should pay for that.
Yeah.
Whether you use it or not, because they're contractually obligated per your agreement to deliver that 5 megawatts should your on-site generation not be able to perform.
Yeah.
And so that's the problem, because people, a lot of customers, residential customers who have solar PV, they don't necessarily have batteries in their garage. But if they have just a net metering, they're actually using if they push their surplus power to the grid, and then when they don't have solar, they pull power from the grid, they're using the grid as a battery. And should they pay for that service?
Yeah, we dove into that on our community solar talk that we did, which is like, when you're net metering, it goes back to that same premise. If everything has to equal each other at all times, that concept of you're going to need the same size grid to back up for 10 hours a year as you do to use it for 5,000 hours a year. It just has to sit there. And if it just has to sit there and you only use it for 10 hours a year, you might as well use it for 5,000 hours a year because it's there. Is the argument. If the cost of the electricity that you're purchasing from the grid is cheaper than what you can pay for self-generation, you got to take into account your investment costs or your financial costs as well as your operating costs when you make that decision. Yeah. And those are some of the dynamics. Yeah. So what do you think is going to happen to net metering then? I think 10 years from now. I think 10 years from now, in a perfect world, you'll see end-use customers, not only industrial customers, but residential customers, see a time-varying rate. Smart meters can do that. Mm-hmm. So if you consume or produce more energy during peak demand periods where generation costs are higher, the cost to supply is higher during those time periods. Mm-hmm. And I think you'll see people starting to make economic decisions regarding when they consume, when they produce, whether or not they invest in storage, based on leveraging whatever resources they may have decided to put on their side of the meter. The bigger challenge becomes, how do you do that from an economic justice point of view? Right. Because
people who have the resources to invest in those type of technologies tend to be more affluent, and you need to make sure that there's some equity in terms of who's benefiting and who can afford to make adjustments. But I think price transparency for all customers, the technology is in place today with smart meters.
Yeah, absolutely.
And if you consume during peak demand, you should pay for that. The last thing the utility wants to see is a customer providing power to the grid at 2 o'clock in the afternoon when they already have more power than they need, and then pulling power from the grid at the same value.
Yeah.
Because it's net metering. From the utility point of view, that doesn't make economic sense.
Yeah. Flo and I, we talked about community solar, and we said, if you want to see what happens when anybody can produce renewable power at any time, variable power at any time, and dump it into the grid and consume from the grid whenever they want, and there's really no change in price between doing that, just look at California. I want to say even 10 years ago, or maybe longer, they would talk about the duck curve concept that
Yeah, it's not quite 10 years old, but it's probably getting there.
Yeah, it was definitely being talked about. If we keep letting people make solar power in the middle of the day and then at night when the sun goes down, you have to have all of this backup power that just sits there all day long that has to then ramp up as the sun is going down right at the end of the day. And I just saw a chart of that. It's getting worse. That ramp is really steep at the end of the day. Am I oversimplifying it to say that basically is because of net metering?
Yeah, I think that's a little bit of a simplification. I think there's a number of dynamics. So one dynamic is power is expensive in California. So there's incentives for people to want to put rooftop solar on their homes because there's a
cheaper.
There's a payback. There's a payback. So what's happening? There's a couple of things. So if you look at it from the perspective of Cal ISO, which actually put out this duck curve, what they see as the load for the state is actual load minus the solar. And so their challenge is peak demand with that scenario occurs in the evening. And of course, solar doesn't contribute to meeting that peak demand. And so during the day, the dispatchable generation resources get more and more constrained because all the solar PV is coming onto the grid. And then when the solar tapers off in the evening, and you see this evening ramp, which last I looked was 13 gigawatts.
That just goes away.
No.
And then has to come out. 13
The
gigawatts.
combination of the dropping off of the solar and the increase in demand, you're seeing a net change of 13 gigawatts of demand in the evening,
That's a lot.
which is pretty significant. To put it in context, that's 13 large nuclear power plants.
Just have to show up.
That just have to show up, which, by the way, nuclear power plants are normally base load. They don't ramp up and down very well.
Yeah.
And so those may not even be running because if they can't produce in the afternoon when all the solar PV is coming onto the grid, they may not be available for that evening ramp. And so that's the dynamic is how do you make sure you have availability of dispatchable generation that's not time and weather dependent to meet a peak demand that's occurring every evening, particularly given the dynamics associated with bringing more solar PV onto the grid.
And going back, not to beat this in too hard, but with net metering, there's no incentive for a homeowner to install a battery to smooth that out.
Basically, they have a battery already.
Which is
it's called the grid.
I'm probably oversimplifying again, but there's probably quite a few natural gas plants out there to do that ramp at the end of the night, I'm assuming.
Capacity, dispatchable capacity becomes an issue. And certainly there's been a major investment in natural gas because natural gas it's not carbon free, but it is cleaner than coal.
It's cleaner than coal.
And it is dispatchable and it can ramp.
At the end of the night.
So it's used for peaking power.
Yeah.
But natural gas is more expensive in terms of investment and operation than wind or solar. From an economic point of view, you might favor wind and solar, carbon-free, lower levelized cost of energy, but people don't turn off all their appliances and their lights at 6 p.m. when the sun goes down. And so addressing that evening peak requires some type of dispatchable generation.
Yeah. Did you know this, Flo? Do you know about this I don't know if many people really know, because you'll see these, whether it's marketing or whether it's some LinkedIn post or whether it's something, some news article that says California made all of its power from solar power at noon on July, or at noon of this day, it had 100% solar power. And I think we lose sight of the fact that there's all of this fossil fuel generation, although cleaner than coal, that just has to sit there until the sun goes down. And then all sort of fossil fuel generation has to come on to fill that gap.
Not running.
It's not running during the day when the solar power is on, but it has to be financed. It has to be underwritten. It has to be built. It has to be interconnected. The fuel has to be made and bought and brought. And so there's this whole supply chain and everything. And I think one of our reasons for starting this podcast was, I think there's just a lot of things in my normal life when I'm talking to my friends that you don't even know that this is happening. You're seeing the high fives and all of the things about how we hit 100% solar, or this company is 100% renewable. And then I just start looking at like the time component. I'm like, not right now, because it's 7 p.m.
And even when you go to 100% renewable, you know what's working in the background.
Wait, say that again?
You go to 100% renewable generation, you know what's working in the background.
What?
You have to have a battery. You have to have something that can maintain voltage and frequency, and you have to have something that can steady or absorb the variation. Even if you're operating at 100%, there is some variability in wind and solar.
Cloud,
Yeah.
a wind speed.
Cloud going over. A single solar panel can lose 80 or 90% of its output in a couple of seconds when a cloud goes over, which isn't a problem if it's only one solar panel, and then you have a million other ones that are not necessarily impacted by that same cloud. The grid forming device, when you're at 100% renewable, typically a microgrid or an island type of system, normally there's a battery in the background, which is the grid forming device, and it's maintaining the voltage and the frequency, and it can provide capacity firming services as well.
Yeah.
So one thing that I think about listening to y'all's conversation about the grid as a battery versus solar farms or having your own solar panels on your house, every state is different. And I think I trust the people in California that they actually care about using the renewable energy and that they're actually doing that.
Yeah.
But what kind of makes me uncomfortable about feeling good investing in solar for my house and being connected to the grid and the whole net metering thing is, are they actually using it? Like, I'm not convinced that they're actually going to use it here in North Carolina.
Use the renewable
solar.
power, the solar that it has to be put somewhere, but it may not be going into a storage
I would
device.
like to know that it's being used and then just rely on the grid for backup instead of the net metering thing where it's all connected in the same. And I worry that it's for naught, or it's for lip service. I don't know.
Yeah. If you're producing more solar in the middle of the day than your house needs,
Well, it's not even going to my house. It's going into, supposedly
it's going into the grid, but they have to do something with it.
And this is community solar you're talking about, or you're talking about panels on top of your roof?
I'm talking about panels on top of my roof, but it could also be net metering also works for solar farms and.
So if you have panels on top of your roof and the sun is shining, there's one of three scenarios. So one scenario is you have more power than your home is consuming, and you just push power to the grid. That power will be used because the power that's on the grid whatever is supplied to the grid has to match and balance whatever is being consumed.
Okay.
So that's scenario one.
Now that you've told me that, I trust you. I needed someone in this industry. I need to hear it from someone personally.
So the second scenario would be solar panels are producing electricity. You are not exporting to the grid for whatever reason. It's going into batteries that are sitting in your garage. So you're storing what you're not consuming so that when the sun is not shining, you can use that energy, and you can, in the evening, for example, you can pull power from your batteries. So you have to oversize your solar, then you have to size your batteries appropriately. And under that scenario, you can operate independently from the grid. If you want to have grid backup, you can. But then you'd have to have a throwover switch and basically then decide, okay, I'm going to pull power now from the grid. The other scenario is if you are producing and your battery is charged and you don't have load, then you just have to curtail, which means you're not taking advantage of the investment. Yeah, turn it off. You're not taking advantage of the investment you have in your solar panels. So that's the other scenario, which if you want to extrapolate that to the grid at large, it's the same thing you see when you have a lot of renewable generation. The renewable generation has to be consumed locally as one option, assuming it's connected to the grid, transmission or otherwise. Address that. It's basically the timing issue, but you have to move the power. If you can't consume it, you can't move it. Next option is you can store it, assuming you have a place to store it. That's local, or now you're back to moving it if you have to move it someplace to store it. Or the last is you have to curtail it, which is economically just not a good solution. And I heard the term, it's actually a company up in Canada, and they're talking about hydro generation. Again, carbon free, but their hydro generation was run a river. And if they didn't have a way to consume the electricity that they were generating from hydro facilities based on run of river, they used the term spilled kilowatt hours, like spilt milk.
Yeah.
It's lost forever. You're not getting it back.
Yeah.
And it doesn't help you out from an economic cost recovery on your investment.
Yeah. They put in that spillway and it just goes past the river.
Gone.
Yeah.
And the same thing when you curtail solar PV, or the same thing if you're not using your wind generators.
So your options with electricity is to use it, move it, store it,
stop,
or shut it off, or spill it. Sounds like spill it is the way to.
So I know this is one of the things that you want to talk about is why transmission? Why the need for transmission?
Yeah.
When we look at that, we are a strong advocate, obviously because we sell equipment that goes into transmission solutions. A lot of the renewable generation, and I'm talking utility scale generation, is not typically located at or near a load center. Take California and North Dakota. Wind is really strong in North Dakota, but there's limited population. There's really not a grid. That power has no place to go. It's not going to be consumed. I don't think there's much storage up there, if any, and there's no transmission. Right. So the first component of needing transmission for renewable generation is just to be able to get access to the grid.
Yeah.
If you're talking about offshore wind, there's no grid off the East Coast, out in the ocean. You've got to bring it back on shore. And so you need that transmission investment to be able to access the grid. The second concern is, in terms of need for transmission investment, is the grid is more or less optimized based on the generation resources we have today and the locations of the load. Now you start retiring coal plants, and even some nuclear plants are being retired, which, by the way, are carbon free. But when you see those retirements, and then you build new renewable generation based on wind in Utah, or wind in the Dakotas, or solar in the desert in the Southwest, you're changing the location of your generation resources, which changes your level of optimization of your grid.
Yeah.
And you may get congestion. You may not have the adequate transmission you need to operate that security constrained unit commitment that I mentioned previously is a concern. Yeah. And then the third concern is this timing issue. How do you match renewable generation with load? How do you match solar, which peaks at 2 p.m. in the afternoon, with demand, take California, that peaks at 7 p.m. at night? Now, think about the scenario where you take advantage of all that wind in North Dakota. Can you move power from North Dakota to California to meet the evening peak? Timing-wise, they align, but you don't have transmission.
Right.
Yep. It just so happens that North Dakota is on the Eastern Interconnect side of the seam between the Eastern and Western Interconnect.
Yeah.
And I don't know if the audience is familiar with the Eastern and Western Interconnect, but the U.S. grid is divided into actually three parts. Yeah. So there's the Eastern Interconnect, there's the Western Interconnect, and there's what's called a seam between the two of them. And then there's Texas, which operates its own grid. All use 60 hertz as the frequency, but they're not synchronized. So that means you cannot directly move power between, for example, the Eastern Interconnect and the Western Interconnect. And the amount of power that you can transfer between the Eastern Interconnect and the Western Interconnect using HVDC, the total capacity of those ties is 1.3 gigawatts.
Jeez. Which,
So-
going back to the duck curve that has to spin up every day, and that's
It's an order-
that's
it's
only
an order-
one-
it's-
that's only
it's
10% of that.
It's an order of magnitude lower than the amount of additional generation needed to meet the duck curve ramp.
In California, yeah.
And so to put that into context, it's basically nothing.
Yeah.
So could transmission help solve that? Sure.
Yeah.
If you could build transmission so you can move power from North Dakota to California, wind in North Dakota starts to ramp up in the evening.
Yeah.
And with the time difference, you can align
Fixes your
that
duck
with
curve issue.
You can, well, it helps.
Yeah.
It helps.
Yeah.
So if you're operating the grid and you're constrained by that security constrained unit commitment and you have a reliability issue, that is what typically has driven new capacity in transmission.
Transmission, yeah.
But California is also looking at, we want to decarbonize. In order to do that, we're going to need transmission capacity. And specifically, they look at three different things. They look at one, more power from offshore wind, which will come in, I think, on obviously the west side of the state, but a little bit to the north. They're looking at bringing in wind from Utah, Wyoming, and that area. And then they're also looking at bringing in power, both wind and solar, from the southwest, coming in through Arizona, New Mexico, and
Yep.
in that direction. So they're looking at transmission capacity not only for reliability, but also to meet their future needs to decarbonize the California grid.
Yeah.
And so a lot of the transmission planning that's done today, though, is focused on reliability constraints in MISO, or reliability constraints in PJM, reliability constraints in New York or ISO New England. What gets missed in that equation is, what about the need for transmission that goes from the Eastern Interconnect to the Western Interconnect
Yeah.
to increase the value of renewable generation? These are some of the things that are behind the big push for transmission.
Yeah.
EEI is supporting that. That's
EEI?
Edison Electric Institute. It's basically an industry organization for utilities.
Yeah.
The ACOR did their, American Council for or of Renewable Energy, I think. But ACOR did a macro report where they looked at the need for transmission. NREL did a report called the SEAMS report, which is looking at the value of transmission, in particular crossing the seam between the Eastern and Western Interconnect. And I think their conclusion was, for every dollar you invest in transmission, you get $2.50 payback and further benefit from renewable generation. So everybody, I think, is on board recognizing there's a need for transmission, but there's some issues that need to be addressed. The planning, we need a national plan, not just a regional plan.
Yeah.
We need to figure out how to do siting, permitting, environmental approvals, that process, the policy piece of it. And then we also need to address cost allocation, who benefits, who pays, and there needs to be alignment in terms of who is benefiting. One of the challenges with HVDC lines is they do have an impact for stakeholders between the two endpoints, but HVDC lines are normally endpoint to endpoint. So people who are selling power, that the line moves, and the people who are buying the power, presumably at a lower rate than what they can buy locally, they benefit. But the people in the middle, are they benefiting? And if they don't think they're benefiting, then it becomes an issue that it becomes an issue that needs to be addressed.
Yeah.
So that's where storytelling and value, basically sales, comes in. There's so many benefits to making the grid more reliable and decarbonizing the grid that are sometimes hard to quantify, but also sometimes easy to quantify.
Yeah.
And are people telling those stories? To make those moves happen easier, to bring people together.
The thing that's weird about energy in general, we've seen it forever, all the way from Ready Kilowatt or any of those old ways that people used to market electricity in the early days of electricity, is just like all of the analysis that you can possibly do, and there's plenty of it to explain why this is good. The reason that it doesn't happen can be as simple as somebody being afraid in the middle of that, like one easement that you needed, and somebody's like, that sounds scary. or not even scary, just like, oh, that sounds scary economically for my land. And it's not a analysis, like no amount of analysis or explaining can get some people over the line. It's just emotional.
Flo, you brought up an interesting point, is what are the dynamics of the grid right now? And we talk about the energy transition. And so what exactly is the energy transition? In my mind, there's two components. So one component is decarbonize power generation. And so I think the current administration has said we want to decarbonize power generation by 2035. I think that's the target date. I think California is saying they want to decarbonize by 2040. So maybe some of these goals are aspirational, but presumably there's an initiative because of the desire to mitigate climate change that we want to decarbonize power generation. By the way, power generation is the second largest source of carbon emissions in the U.S. So the question is, where are we today? What's our level of decarbonization of generation today? And the answer is we're about 40% carbon free with our generation today. So 20% of the total, or half of the carbon free generation, is nuclear power, in rough numbers. And the other half is a combination of hydro, wind, and solar. There's also some biogas and tidal and other sources, but the main components are hydro, wind, and solar. So then you have the other 60%, which is not carbon free, and presumably that's either going to be cleaned through carbon capture or it's going to be replaced. So 60% of our generation in the country today, between now and 2035, needs to be replaced or needs to be implemented with carbon capture to clean it up, which think about the challenge of doing that. We're talking 12 years if it's 2035 to replace or clean 60% of this country's power generation. So that's the magnitude of what we're talking about on the power generation side.
That's just replacing what's there, but then there's also the question.
I'm going to get to that in a second. That's a good point. So there's a tailwind behind renewable generation in terms of wind and solar, because wind and solar have the lowest levelized cost of energy of any generation investment alternative today. So I view that as a tailwind. The challenge is it's not dispatchable. It's time and weather dependent. And right now, our load is not aligned to exactly match renewable generation, particularly when you have a week of rain or an extended calm period. So having carbon-free dispatchable generation is going to be a key challenge to achieve that decarbonization of power generation. So people are looking at hydrogen, which is really basically a storage mechanism. If we're looking at using electrolyzers to produce carbon-free hydrogen, which in turn is then used for dispatchable generation, it's really just using hydrogen as a complementary energy path in storage. But we need to find a way to have dispatchable carbon-free generation. People also are looking at modular nuclear as another potential. But let's park that for a second. Now let's look on the consumption side. So electricity today is about 20% of energy end-use consumption. And what's forecasted, Europe is saying electricity consumption is going to double between now and 2050. In the U.S., the last analysis I saw was done by NREL, and they were forecasting at this particular study, which is I think a few years old, 80% increase in electricity consumption between now or between 2018 and 2050. Wow. And so where is that coming from? It's 29% increase, just organic increase, population, maybe more data centers. Just
electric vehicles, maybe, not even those.
Let's exclude electrification for the moment. Just population, more uses of electricity aside from electrification. But that growth, 29%, over 30 years is less than it's slightly less than 1%, which is pretty low growth. Maybe crypto mining is going to push that up a little bit. But certainly some of the data analytics, data management is driving increased demand, but you also have offsets with energy efficiency. There's some population growth, et cetera. So that's growth, but not counting electrification. Then electrification is going to drive increased consumption by 40%. So if you take roughly 1.3 times 1.4, that's where you get the 80% increase. The bulk of that increase is transportation under electrification. Yeah. There's buildings, there's industrial, but the bulk of it is really transportation, which, by the way, transportation is the number one source of carbon emissions in the U.S. So if you're going to do anything to reduce carbon emissions, the two elephants in the room are power generation, which is slightly less than 30%, and I think transportation, which is right around 30%. So between the two, you're about 60% of our carbon emissions are related to those two components. Now, what's interesting with electrification, and I said it's going to approximately double between now and 2050, recognize that's doubling consumption. Okay, and so consumption and demand, or peak demand, are not the same thing. And so that means if we can manage the charging, we can utilize some of the excess capacity that exists in the grid today during lower peak demand periods, increase the utilization factors of our generation and our T&D infrastructure, and maybe not have to double the capacity of the grid, even though the consumption is doubling. If that makes sense.
Yeah. Yeah, it comes down to like where and when, like being able to take what we make and then change where it is and when it's being used.
And so we were talking a little bit about California with solar PV in the afternoon and possibly being curtailed because there's too much of it, and in that evening peak that occurs in California in the evening. So what if you could make sure that there was no electrification or vehicle charging at 8 p.m. and instead you try to do as much vehicle charging at 2 in the afternoon so that you're managing the capacity that you have. So I think that's important when you look at the energy transition, to look at both of those. How do we decarbonize generation, and then how do we electrify end-use energy consumption to reduce carbon? There's going to be things that are difficult to electrify, though. Yeah. Long-haul heavy freight on trucks is going to be difficult to electrify. Yeah. You end up carrying more batteries than you do cargo. So from a weight perspective, and I'm exaggerating to make a point, but that's something that, because of the long distances traveled and the weight involved, and to recharge those can take a fair amount of time. Yeah. So that's certainly not the low-hanging fruit. Yeah. But local delivery trucks, distribution trucks, those, they don't go more than maybe 150 miles in a day. So you can size the batteries. You have dwell time at night to do the charging. So that makes sense to electrify as quickly as possible.
I can imagine like an app on your phone that notifies you when it's a more affordable time to charge your car.
That technology exists today.
Yeah. Go charge your car right now at 2 p.m. because the grid has more power than it needs. The generation isn't matching the load.
But again, that technology exists today. You can have an app on your phone that can control when you charge your car and turn your car charger on and off remotely. Yeah. So the only piece that you, quote, are missing is knowing the time of use rate for electricity. And that's pretty predictable as to what rates are going to be on a daily basis. So you know what the hourly cost of electricity is going to be, and you can determine or schedule through an app when you charge your car. Wouldn't it be nice? The technology is here today to do that.
That's what's so mind-boggling about it, is all of this technology we're talking about. It's not like we're sitting here saying, can you imagine some miracle in the future where, if we were talking about healthcare, we'd be talking about, a cure for cancer. The cure for all of these things we just talked about is already here. Like, the storage is here. I know there's costs and all of that. So that's where I want to go next, is the pesky part of this equation is the people in politics. Okay, if we want to decarbonize by 2035 and transmission is an important part of that, moving power to where it needs to go, using the renewable energy, making it where it should be made, North Dakota, and moving it to where it needs to be used. What's the average time it takes to lay a transmission line from a place like North Dakota to, say, California?
Oh, I'd
Through the
say
Rocky
average
Mountains.
time to get a transmission line from start to finish is probably 10 years, give or take. Maybe longer, maybe less, but to go through that entire process. Because first you need to define the economic value. So economic value historically has been the need for the transmission to address a reliability constraint on the grid, but now we're supplementing that with the economic benefit of being able to move power from point A to point B, whether it's renewable or whatever the case may be. There's economic value in that.
Yeah. And you really open up a market in a way, right? Like on both, I've only briefly interacted with the Empire Connector. Did you guys work in the Empire Connector, or was it the Champlain Hudson?
Well, we are working now on the Champlain Hudson
Got it.
connector. That was something that I believe was started last year. So
Yeah.
we're working on that project.
And what about, so you said 10 years, is that 10 years from the start of proposing that as a project to the end of it being built? Or is 10 years from the start of once it gets approved? Or
No,
yeah.
the actual construction time doesn't take 10 years.
Right.
But
the permitting and
it
the
actually takes longer.
easements
That
and
takes longer than the actual time
That's what I figured.
to construct.
what is that process like? If we were sitting here today and we decided, hey, that transmission line from North Dakota to California, that's a really good idea. We should go and do that tomorrow.
Yeah.
What would you do tomorrow? What would you wake up and do tomorrow?
I think the first thing you need to look at is the economic viability at a high level. What value is this line going to provide? Again, as I mentioned, historically, it was addressing a reliability constraint. Today, it could be addressing market congestion or being able to just enable higher utilization of renewable generation connecting to the grid. There needs to be that economic driver that just makes the project viable.
Yep.
The next part of that is looking at the routing, looking at the land and access to the land and securing land rights, because if you don't have the land, you're not going to be able to build it. What follows that is getting the permitting and addressing their environmental requirements, et cetera. And that's where you have multiple stakeholders. You have federal stakeholders, you have state stakeholders, you have local stakeholders, you have industry groups, conservation associations.
Yeah.
You have an abundance of stakeholders. You have to navigate that process. And assuming you can do that, then there's also the financing. Is there a PPA? What's the cost recovery look like?
Yeah.
You know, how is it going to be? How are you going to recover the cost allocation? Who benefits, et cetera? There are those issues.
Yeah.
So if you can get through all of those, then in theory you can start constructing.
Applying for permits.
As long as, you need to apply and make sure you have the permits,
Yeah.
because starting construction obviously represents a significant investment.
Yeah.
But even that process I just outlined costs tens of millions of dollars
Just to get to this.
just to get to the point where you want to start actually building.
And the answer could be no during that process. So you
And
could
the
be out
answer,
10 million bucks.
could be no.
Yeah.
And sometimes the answer changes and then goes from yes to no back to yes.
So
There's an example in New England of that, but it's a risky process. And that's, I think, the biggest issue that needs to be addressed is the risk.
yeah.
How do you embark on a project like this, not knowing whether or not you're even going to be able to build the transmission line at the end? And all that money you invest up front, maybe the project may be killed at the last step. And so there's a risk element, and there's some monies that have been included in IIJA, for example, or the BIL, to facilitate transmission, looking at maybe backstopping right-of-way acquisition potentially. That was something that was passed in previous legislation, but needed to be reworked. I don't think that's yet been implemented. Maybe guaranteeing loans for transmission lines. I don't think the capital, though, is the issue. I think if you could address the risk,
Yeah.
and if you have the financial value behind the line, the economic value, you can get the money.
Yeah.
In my opinion, I think the real risk is that siting, permitting process, the policy,
Yeah.
the levels of regulation
Yeah.
is really where the challenges are.
Is there an opportunity to use the rail way network or the interstate network?
Yeah, I think there's one line, it's called the Sioux line, that's looking at rail right of way, using a cable and going underground along rail rights of way to possibly facilitate. Because at some point, if there's strong economic value, then even though you have to pay more to maybe take a longer route to follow rail, and you have to go underground with cable, which might be a little bit more money, but if at the end it still pencils out, then the project is economically viable, and it may be easier because it's out of sight. You're dealing with fewer landowners if you're dealing with maybe 3 or 4 rail lines, for example, and you're not impacting the ability of their property to perform for their in-use purpose.
Yeah.
You're just trying to move more power down existing rights of way is another avenue.
Yeah, that's what has struck me for definitely the last decade. I think a big epiphany for me in the clean energy space was that so much of what we are going to use to generate electricity is technology. It's not fuel driven. It's not commodity fuel driven. We're not extracting things in order to put it. So now being able to skip the extraction part, we can take some of that money that used to, because that's pretty high risk money to show up to a piece of land and hope that your geological models are going to produce oil for you. Somebody took that risk at one point, and it sounds like now that the technology costs of clean energy are coming down, or have come down almost 99% since I got into this business, even a decade ago, or I guess now it's 13 years ago. It was like unreasonable to install a solar panel. You're crazy if you were going to do that. You needed all sorts of subsidies and programs. But now, I guess just finding that capital that will take the risk on transmission, because if you do get the line, as you said, it's almost like finding oil in North Dakota. If you could get a line from North Dakota and you could take the risk, the $10 million, $20 million planning risk to get a line from North Dakota to $50 million planning risk, $60 million. Do I hear 70? Do I hear 80 million? Sold to Gary. Yeah, I think that if you're willing to take that risk, it really would be the equivalent of finding or unlocking this value. But it does seem like a lot of the risks that were taken in oil and gas hasn't sort of translated over into renewables as much.
Maybe not as much, but I do think there's some analogies, as you pointed out. And what's interesting is, if I take as an example an HVDC line using cable technology, that technology is mature. We're continuing to ramp up the ratings of those lines. Now, I think we're well over 1 gigawatt. And depending upon the technology, I think this might be with overhead HVDC, we can go 2-3 gigawatts of power. I think it's Grid United and also Elite just announced a project, and it's the North Plains connector or Northern Plains connector. But anyway, it's to connect the Eastern and Western interconnect. And the Eastern interconnect, 2 tie points, one with SP, one with MISO. And it's basically to be able to move power from North Dakota into the Western Interconnect. I think it's about 300 miles long, 3 gigawatt rating, $2.5 billion estimated cost. So major project.
Yeah.
2 quick questions about transmission lines. We talked about this last time, and for some reason I thought it was interesting because I had no idea how big they were. And you explained they're not that wide.
Okay, so we were talking about cables when I said they're not that wide.
Okay.
And so through 2 cables, 10 inches each in diameter, give or take, you can move over 1 gigawatt of power.
So you can take like a nuclear power plant, the old school ones.
And then think about it.
And move that through.
Yeah, so think about building a 400-mile extension cord for a nuclear power plant, and you need 2 cables this big. And for people who can't see, that's about 2 cables, maybe 10 inches in diameter.
Yeah. Smaller than a dinner plate.
Or maybe, I used to have some samples in my office of HVDC cables, but they're not gigantic. They're definitely less than a foot in diameter, maybe even only half that.
Yeah.
But depends upon the technology that you're using for the insulation and type of cable.
And when you say it can move 1 gigawatt, over what period of time? Like how quickly?
So a gigawatt is a rating.
Okay.
So it's like a rate of power movement.
Okay.
And then a gigawatt hour is the amount of energy that's actually moved in 1 hour when the rate of power flowing is 1 gigawatt. So gigawatt is a rate, and gigawatt hour is an energy. That's why when you look at batteries, battery energy storage has 2 ratings. One is the rating of the power conversion system, which is the rate at which the battery can either be charged or discharged. And that might be a 1 megawatt battery, which is the power electronics. But then the amount of energy that could be stored, if it's a 1 hour battery, it would be 1 megawatt hour. If it's a 4 hour battery, the amount of energy that gets stored is 4 megawatt hours.
Okay, cool.
And so the rating of a transmission line, since you're not storing energy, you're not really consuming energy, it's a rate at which energy flows down the power line.
What would 1 gigawatt power?
A gigawatt is the equivalent to the output of a nuclear power plant. So I don't know how many homes that would be, but it's a lot.
Okay.
It's a lot.
It's a lot.
I want to say like 200,000.
Yeah, I was going to say you could power a whole city probably with a 1 gigawatt nuclear power plant.
Yeah.
Cool. All right,
So-
thank you. I just wanted to put that into.
Yeah, actually, how many people? Yeah, if you had 2.5 people per home or something like that, that's probably a 500,000 person city.
I don't have those numbers memorized, but they're readily available.
Yeah.
You can easily find that on.
Chat GPT.
Yeah. They might script the whole podcast. But
You could ask it all these questions.
there's one interesting application because we were talking about what could help the grid operate, and you mentioned the Champlain-Hudson line,
Yeah.
which is bringing hydropower down from Canada. So we did a project over in Europe. The line is now commissioned. It's an HVDC line. It goes, again, 300 or 400 miles. It operates at 1.4 gigawatts, and it connects Germany to Norway. And it's bidirectional. Germany has excess wind and excess solar. It doesn't have to worry about curtailing it. If it can't consume it, it can ship power to Norway. So Norway can then use that power, but in the process of using that power, they don't consume their hydro resources. So they can build up water behind in their reservoirs or behind their dams because they're utilizing the power that's coming from Germany. And so they now have surplus water stored, which Germany can then tap into by reversing the flow in the line when they don't have wind and solar surplus. And so the basic concept is it's a huge 1.4 gigawatt water battery. Now you say, oh, that's over in Europe. But in theory, we could do the same thing here in the US, but we would need a partner like Canada, which has tremendous hydro resources. And if you couple that with our wind in the center tier of the country, going from Texas to North Dakota, and the solar in the southern half, particularly the western southern half, you have the ability now to have some diversity in your carbon-free generation with hydro from Canada, wind and solar in the US, and by managing how much you build and how you operate, you now are getting to that point where you're moving closer and closer or enabling more carbon-free generation resources.
Yeah.
And so that's conceptual. There's policy issues. There's issues about moving power over a border. Who owns it? Who operates it? Who takes the risk for it? The planning, geopolitical risk, all of that comes into the mix.
Yeah.
But from a technical point of view, we could start building that line tomorrow.
Yeah, that's amazing. It seems like, I read an article in The Economist that the picture on the front is somebody hugging the pylon, basically the high voltage electricity tower, and it was basically making the case, like, if we want to have a clean, 100% clean grid, everybody better get used to seeing these really tall towers. And you're making the case that we don't need to see those really tall towers. Those HVDC lines, at least the one you mentioned in Champlain Hudson, that most of that's underwater.
That's underwater.
Right?
That pretty much runs underwater the whole way, so you won't see it. Now, that one that's in the North Plains, that I believe that would be an overhead line at that 3 gigawatt rating.
Yeah.
Or you could run, in theory, you could run 2 parallel circuits at 1.5 gigawatts and put those underground if you were so inclined to do so.
And that's probably this might be a stupid question, but with HVDC, do you have to pick one or the other, above ground, below ground, or is it different types of technology to run above ground?
There's a couple of different types of technologies. I think there's the converter technology that's could be different. I think LCC, line commutated. I do know that what we're using today for underground cables is voltage source converter technology. And actually, we used to use thyristors as well. And so now the voltage source converters the losses have improved dramatically. The costs have come down. So now the controllability is much better with the voltage source converters. And so that's what's typically being used. Well, definitely for the cables.
So when you say if it's a 3 gigawatt overhead that I can run long distance.
Yeah, that might be using a little bit different converter technology in its overhead.
Got it. Yeah.
But don't quote me on that. I'd have to get you some information on that.
Yeah.
But you mentioned something about hugging a transmission line.
Yeah.
There's nothing more beautiful than a transmission line tower with the sun silhouette behind it.
I agree.
At sunset. It's all in the eye of the beholder.
Yeah.
When we travel on trips and we're using the car, every time my wife sees a substation, she goes, "Look." And I say, "A thing of beauty."
Yeah, exactly. We used to go out before we moved down here. We lived in an area outside of Seattle where it's this amazing place to go for like brunch, and it overlooks this hydroelectric plant. It's this amazing waterfall. But then, like right next to it is right next to the valet is this huge substation, and I always used to take my wife to sit next to the huge substation for our romantic dinners. It's like, we're going to the power plant for dinner. I agree with you. I don't know if the
ambience from the hum of the transformers, right?
Yeah, exactly. I don't know. That's why I was so excited to talk to you today on this, because I was like, there's just not too many people who find the beauty in large-scale industrial power systems like I know you do.
Wow.
I feel like there's so many people that it's like connecting these things together between cleaning the grid and these are massive, as you said, like geopolitical issues that if we could, this is always like the technologist's viewpoint, right? Is if we could just get everyone to see that this could work, then everyone would agree. Yeah. But I do think they're overcoming those issues is where I don't know. Do you have an idea of how to overcome those issues, or do you just put them in that bucket of maybe somebody can figure that out?
I think we're making progress. Certainly, there's been technology advances. We were talking about HVDC, higher voltages, which means more throughput, lower losses, which means better efficiency. So technologies are continuing to advance. Maybe not to the extent that we've seen in terms of price drops for solar PV panels, or even the cost of lithium-ion batteries has dropped from where we were 10 years ago dramatically. There are technology advances, and I do think the technology will continue. But I think policy is an issue. Policy matters.
Yeah.
And if you look at, for example, the production tax credit, which stopped for wind a number of years ago, and it stopped investment. And so today, I think there's recognition that we need transmission. More and more people are starting to embrace the concept of we need transmission investment if we are going to decarbonize our economy. The government is, regardless of your politics, the government is putting a lot of money behind renewable generation. It's putting a lot of money behind hydrogen. It's putting money behind battery technology. It's even putting money behind modular nuclear. Money moves the needle. Hopefully it moves the needle efficiently, that we efficiently use this money. But with the production and investment tax credits that are backing renewable generation and some of the incentives behind hydrogen, I think we're going to see changes over the next 5, 10 years. Yeah. So I think that's what's going to be critical. Can we turn the corner, get broader support for the investments that we need in the infrastructure like transmission, and can we close some of the gaps on economics like hydrogen? Green hydrogen is $4 a kilogram? With the incentives, you might be down to $1 a kilogram. And now all of a sudden you're on par with gray hydrogen, which then could be used for feedstock or could be used for long-term storage or even just load shifting for electricity. So I think we're going to see those changes. Yeah. Maybe not today, but in the next 5 to 10 years, I think we're going to see some dramatic changes.
Are there incentives in the Inflation Reduction Act for transmission as well, or no? I don't actually
I'd
know.
have to check and see. I know there's incentives in investment in transmission and the Infrastructure Investment and Job Act, which is also what the bipartisan infrastructure law. Yeah. So I know there's segments and sections in there to invest in transmission, both in terms of some of the policy and the backstopping, as well as in reliability and resiliency.
Yeah.
Now, how that money gets funneled, some of the money is going to states, some of the money is going to rural investment. Navigating that, we're still working on that. There's a lot of guidance documents which have come out related to the laws, which are basically providing some guardrails for the investments.
Yeah. I'm going to ask you one more question. Unless you have other things that you would like to,
go ahead.
To say. We've covered so much ground here. I think what is super heartening about the conversation we had today is that we don't need miracle discoveries to figure out how to do these things that like decarbonization or having more resilience against these things. But coming back to the policy question, let's say for a moment you get to wave a magic wand, or let's say you go through the process of becoming a politician. I don't think that's on your roadmap. And you could propose a bill to speed up the energy transition. What would that bill include?
I guess three things jump to mind, and two of them we've already talked about. Finding a way to, address policy or incentives around transmission and also around storage. Transmission to enable movement of power, give the grid flexibility, connect new generation resources. And storage, it just gives you operational flexibility. It really decouples that supply from demand, which always has to be in balance, and it just gives you whether it's capacity firming or shifting generation or shifting load, or there's probably 8 different use cases for storage. Mm-hmm. But the key thing is it gives you operational flexibility and it decouples consumption from immediate demand. And so driving transmission investment, driving storage investment, and the policies behind that and incentives behind that are 2 things. Mm-hmm. The third one is more controversial. It's, should we have a carbon tax? If we want to decarbonize, should we make carbon expensive so that people look at other alternatives and the economic attractiveness of other alternatives increases if carbon becomes more expensive? And so there's a lot of issues associated with that around economic impact, economic justice. But if you really wanted to change things, make carbon more expensive. But that may not be economically attractive or viable or politically acceptable. Yeah. So I'll fall back to transmission.
Yeah, that's what you put the carbon tax in there so you can negotiate against that one and still get your number 1 and 2.
I've seen forecasts of the cost of hydrogen. They're looking at the breakpoint between blue hydrogen, green hydrogen, and gray hydrogen. Well, the curve for gray hydrogen was, rather than being flat, was showing an escalation. And they said, this is caused by the carbon tax.
So they're already baking it in.
So at least this one source of data was baking in a cost of carbon, which was going to make the economic attractiveness of either blue or green hydrogen that lowers the hurdle, so to speak, where it's now more either economically viable or more attractive because the baseline, which is gray hydrogen, is going to increase in cost over time because of some cost of carbon. We'll see if that happens or not, but I hesitate to mention that at times because there's a lot of political issues and justice issues associated with increasing the cost of a key. You're increasing cost of energy. That's going in the wrong direction. I think from an economic point of view, if we can find a way to be the leader in low-cost, clean energy, that's a win for everybody.
That's huge.
When you were talking about the carbon tax, it occurred to me that probably in this report you saw about hydrogen and the different options. There is no actual carbon tax, but it's the idea of the projected cost to society on climate,
Yeah, so there are associated costs to carbon emissions that do impact the economy from health, et cetera, which is one of the reasons for decarbonizing, in addition to the impact to climate change, because there's obviously impact from the costs of climate change. But I'm not sure that we have a specific carbon tax yet. There are costs to the economy associated with carbon emissions, but I don't think we have also said we're going to put a carbon tax on natural gas or anything like that.
So the concept could be used literally or more figuratively. I think in both ways it's useful. When you originally brought it up, I assumed it would be like a literal carbon tax.
There are certain countries that are looking at that, and there may be even states in the U.S. that are looking at it.
Yeah.
There's a partial reason why gasoline is so expensive in California. It's taxed, and it has high taxes on it. Now, whether or not that's to discourage use of gasoline or not, I'm not going to go there. I don't know.
Yeah.
But
that's tricky though, right? Because if you have low income or even fixed income and you can afford a certain amount of gas per month to go to your job, and then they say, oh, sorry, it's now going to be $80 to fill up instead of $60 to fill up, then that's coming straight out of the bottom of the line and the person who has to get to their job.
So there are impacts, and you got to make sure that you're not distorting the economy. I mean, just look at when diesel fuel went up to $5 a gallon.
Yeah.
People said, well, that's driving costs of everything because most things get moved by a truck.
Correct, yeah.
And then that drove inflation, and then inflation drove the Fed to raise interest rates. Has that had is there a cost to all of that? An economic cost?
Yeah, diesel isn't just the people who want monster trucks with big tires. Yeah. I'm always hoping for the technology cost curve to keep coming down and somebody figures out how to leverage that. That we're not going to get into this today, but if the technology keeps coming down in price, it disincentivizes people to jump into the stream today and sign a big contract based on today's economics. But let's not forget, cellular companies and cloud computing companies have figured out the correct business model to leverage that decline in cost of technology. Let's see an electricity company do that. Please.
So anyway, policies that encourage transmission investment, storage investment, and then the continuing, I don't know if you need external drivers for this, but just the digital technology investment.
Yeah.
The other thing that's also changing the grid is power electronics.
Yeah.
Batteries, solar, wind, they all get connected to the grid through power electronics. HVDC is power electronics. So that's also changing our grid.
I have 4 new episode ideas, by the way. We might have to just keep inviting you back. Okay, we're going to close on that. Thank you so much for making the long drive over here.
Yes, 3 months. No, this was fun.
Yeah.
Thank you so much.
Thanks for tuning into this episode of the World Changing Podcast. Be sure to follow us wherever you get your podcasts, Spotify, Stitcher, YouTube, to hear the latest episodes.